Well, well, well. Let's work on this problem. Rotating image. So, given an n by n matrix of integers matrix, rotate it by 90 degrees clockwise. Must rotate the matrix in place. Do not allocate another 2D matrix and do the rotation. In place. Okay. Sure. You do it in place, is it not? Like what? 2 goes to... Or 1 goes to the next. 4 goes up. 7 goes up. Kind of think 5 just stays where it is. I feel like there's some algorithm which makes it O of 1 space complexity and O of n time complexity. Well, actually, O of n squared time complexity. I can't necessarily think of a solution which would make that work. I mean, it comes down to specifying exactly what happens where. So at index 0, you move to index 1. At index 2, you move to index 3. So at index 1, you move to index 2. At index 2, you move to index 5. At index 5, you move to index 8. So if it's an n, if it's not an n, move it to the left. If it's really an if this then that, no? It really feels like it. It really just feels like an if this then that type problem. If you're in the middle, you need to care. Yeah, no, I can't figure this out. Well, rotation. How do you do a rotation in math, right? How do you do a rotation in geometrically? Should be a transformation, I guess. That makes it rotate. But yeah, no. I can't think of any solutions here. I'm gonna look at the solution. Brute force, rotate by 4 cells, reverse and transpose. The flip, reverse and transpose. Rotate by 4 cells. By 4 cells. Okay. Right.
Hey everyone, welcome back, and let's write some more neat code today. We're given an n by n matrix, so this time it's a square matrix for sure, representing some image, and we want to rotate that image by 90 degrees clockwise. And we are required to do this in place, so we cannot allocate more memory. We can't just make a copy of the matrix and rotate it like that. So the challenge here is definitely doing it in place. You can see that they had a original matrix like this. What they did is they took the 1 and put it over here, so 90 degrees. Basically what they did is took this entire first row and moved it into the rightmost column, right? And so they did that by moving this over here, moving this 2 over here, moving the 3 over here. And so the problem is when you're moving this 1 over here, you have to save the 3 temporarily, right? So you have to save the 3, or once you move this 1 over here, you can take the 3, save it, and move it over here. And we know that this entire right column is going to actually be put in the bottom row. So what is actually going on is this 9 is actually being moved over here, right? That's where it ended up in the result. And then this 7 is being rotated over here. So that's where the 7 ends up. The 1 ends up over here. The 3 ends up over here. The 9 ended up over here. So these 4, let's say, have been rotated so far. So now we don't have to touch them. But you can see there's a little bit left in the outer layer. So let's just worry about the outer layer so far. We don't have to worry about the 5, but in the result, we know that the 5 actually doesn't move. You know, you rotate it. But what about this 4? Now, it's basically the same thing that we did over here, right? We are rotating this. So basically, we can think of it as being in the top left, right? The original square we were rotating was like this. Now the square we're rotating is like this.
Yep.
It's still technically a square, you know, if you turn your head a little bit, but this is what we're doing. We're rotating this. So this 4 is of course going to be moved over here to this 2. And before we get rid of the 2, we want to save it and move it over here to the 6. And so in the original, we have a 2 over here, but we know that 2 is going to be rotated, right? Because this is the rotation we're doing. And before we get rid of the 6, we want to save it in a temporary variable and move it over here, replacing the 8. But we don't want to lose the 8 yet because it needs to be rotated as well. It's going to be rotated over here to this 4. And since we rotated the 2, we know there's going to be an empty spot over here for the 4 to be placed in. And that's what you have over here, the 4. The 2 got moved over here. The 6 got moved over here. And the 8 got moved over here. So this is still a rotation.
Yes.
And lastly, we just have a 1 by 1. We know that, you know, it can't really, rotating it will just be the exact same. So let me show you the general algorithm to solve this problem. We're going to do this in n squared time, meaning we only have to look at each cell in the matrix once. Remember, the dimensions are n by n. And we don't need any extra memory, so the memory complexity is going to be constant. We're doing this in place in our given matrix. So I like to set some boundaries. So we know that this is our left boundary and this is our right boundary initially, because we're going to rotate the outermost layer first, right? The outermost square, and then we're going to move inward, right? We're going to do the inside of the matrix. And the top boundary I'm going to place over here because that's the top. Remember, the origin over here is 0 by 0. This position is 3 to 3. It goes like this, and as you go down, it increases. And the bottom boundary is going to be down here. So immediately we're going to start the rotation. Now, how is the rotation going to go? Well, let's start at the top left because it's the easiest, right? We know that this is the general rotation that's going to take place, right? Because we're going clockwise and then we're going to do that, right? And we know we're going to keep doing that with every element in the top row. So we did the first element in the top row, then we're going to rotate the second element in the top row. And how is that going to look? Well, it's going to be pretty similar. So since this was the second position in the top row, we're going to move it to the second position in the last column, right? So in this column, we're going to rotate this one to this position. So the second to last position in the bottom row. The main thing to notice though is that this is offset by 1. This is offset by 1 from the top. This is offset by 1 to from the right. And so the position that it's moved to is also going to be offset by 1 from the bottom, which is where
For sure.
the last rotation took place. And then this is going to be moved over here. And so as you can see, we have one last rotation to make, right, with these 4 elements, and they actually do form a square if you tilt your head enough. This is a square rotation, a matrix rotation.
I mean, everything's a square rotation,
Notice how, since we already rotated this one, we're actually not doing 4 rotations for the outermost layer. We're doing 4 minus 1 rotations. We're doing 3 rotations, right?
Yes.
So even though the outermost layer was n by n, we actually did n minus 1 rotations, right? So we did 3 rotations. And let's say after we complete the outermost layer, right? Let's say we've completely rotated that. You know, we had to rotate this part, and this part. So once we do that, then we know that we actually have an inner matrix that we have to do. So we did the outermost layer, but now we have to do the inside. How am I going to handle that? Well, it can actually just be treated as a subproblem because we know no matter what, it's going to be a square matrix. So all we really have to do is take our pointers and then shift all of them by 1. So our left pointer will be shifted here, our right pointer will be shifted here, our top pointer will be shifted here, and our bottom pointer will be shifted here. And so now the last rotation seems pretty obvious, right? So it's going to be 1 rotation, it's going to include 4 elements, and then we will have our result. Now, one last thing I want to show you, and then after that rotation has taken place, we know we can update our pointers one more time. But at this point, what we'll notice is our left pointer is over here and our right pointer is here. We know that left should always be less than right, and since these pointers have crossed each other, we know that we can stop the algorithm, right? We don't really have a matrix left to rotate. Okay. One last thing I want to show you about the rotation is we know that the top left is going to be put in this position, right? The 11. So we're going to cross that out. So we're going to really replace this with a 5. But then what happens to the original 11 that was placed here? Well, what we can say is, oh, let's move the 11 to a temporary variable.
Of course.
And now let's put the 11 over here. So we're putting an 11 over here now. But what happened to the 16 that was over here? Well, we have to put that in a temporary variable, a 16, and then move that 16 over here. So let's replace this with a 16. But what happened with the 15 that was over here? Well, we moved that to a temporary variable. And now that temporary variable 15 is going to be placed over here.
Okay.
So the 15 is here, and we don't have to move the 5 to a temporary variable because look, we already put it over here. So we're needing a lot of temporary variables. I can show you a slight improvement to this, which isn't required or anything, but I think it makes writing the code easier. So we know that this 5 is going to be rotated, but let's do the rotation in reverse order. So instead of moving the 5 over here first, I'm going to take the 15, which we know is going to be placed over here, and I'm going to put the 15 over here, and I'm going to move the 5 to a temporary variable. Okay, so are we going to move the 5 over here now? Nope, that's not what we're going to do. We're going to do this in reverse order. So since the 15 has already been moved, let's take this 16 and move it over here. So now let's replace this 15 with a 16.
Okay.
And now we know that we need to make a rotation from 11 to here. So let's put an 11 over here. And last but not least, we know that the original 5 had to be put over here, and we stored that 5 in a temporary variable. So now let's move that 5 over here. And so we did the exact same rotation, but do you notice how we did it in reverse order, right? We went counterclockwise, and the thing the reason that was helpful is we only needed 1 temporary variable,
for sure,
which will make the code a little bit easier for us, but it's not actually required. The overall complexity is still the same. The memory and the time complexity is still the same. So now let's get into the code. So the first thing I'm going to do is...
I think I know how to write the code. I will need to write it myself. I'm just also thinking how the brute force hero works. I want to look at these solutions. Space and time complexity builds out, so this space complexity is n squared, because in rotated, everything is initialized to 0, And then you make rotated j n minus 1 minus I. Wow. Excuse me. Excuse me. How does that work? If I just look at the problem, I would understand it. If I look at an example, right? So if we have j is 0, I is 0, n minus 1, so 0 up to say 3, right? 2. 0, 2 is equal to the current ij. And then 0, 3, so 0, so j is 1. If j is 1, and n minus 1, I can see how that works. Yeah. I can see how the brute force is a way to solve this problem. So even if you had 2 and 2, if you had 2 and 2, 2 and 0 is equal to 2 and 2. 2 and 0. Two and 0 is equal to 2 and 2. Yes. Right. Right. Right, right, right. Okay. The formula then kind of seems interesting to make note of. So rotate image. The general formula for rotating an image is rotated now this isn't technically called a formula, but whatever. We get it. Alright. Cool. And then the rotate by 4 cells option. Because it's a square, that's why you can rotate by 4 cells. Sure. That'll be something I can figure out. And then reverse and transpose. You reverse the matrix vertically. How do you do that? Reverse the matrix vertically. And then transpose the matrix horizontally, perhaps. Ij, ji is equal to ji, ij. Transposing for sure. I can see how that is being transposed. Yes, and you're only doing the top half. For sure. Reverse and transpose make sense. It does make sense. Reverse and then transpose. Why not just transpose? Because if you were facing, say, up-oriented, transposing faces down to the right oriented. Whereas if you're up oriented, flip, and then transpose. Oh, that's flipping horizontally. If you flipped vertically, and transpose. I see how that works. Wait. No, if you had top, sorry. If you had top, right? Vertically transpose. Interesting. Reverse. Vertically reverse. I gotta. Let me do this in a terminal. So say our matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Now matrix reverse. Okay, I just reversed it. So what's matrix? 7, 8, 9, 4, 5, 6, 1, 2, 3. Oh, Robert. This is my first time seeing you without a jacket. Really? I haven't worn a jacket in a while, actually. Henry, these 2D arrays are what appears in my nightmare sometimes. Perhaps. I wouldn't be surprised, because they are kind of interesting. Okay, but matrix reversing does that. And then you're saying to transpose, right? So let's run this for I in range, len a matrix. For j in range, len of matrix. J in range, len. Ooh, actually. I in range. Oops. I wonder if you can do this for j in range. I plus 1 len matrix. Let's see. Tab. Oh, that does seem a little too much. And then you're doing matrix ij matrix ai is equal to matrix ji matrix ij. The matrix now is 147, 258, 369, where we can now matrix reverse. Whoops. 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Kind of rotated it the wrong way, so I rotated the opposite way. Obviously then, I did this, followed by this, followed by this. Ugh, I'm kind of going the opposite way. Still. And then I did a matrix reverse again. What's matrix? 7, 8, 9, 8, 7, 6, 5, 4, and 3, 2, 1. Okay. That's nice to know. That's nice to know. So you can reverse vertically, then transpose to rotate left. Reversing vertically will have this effect, whereby I show a screenshot of the command line output. So if you have a matrix and you reverse, get this. Okay. Nice. Big. Alright, so now I want to just quickly write the approach that was explained now by the Leetcode. Okay, so I'm not going to look at that solution. Right, I know the video explanation is here, but I'm not going to look at the solution coded up. I'm going to try this. Because now that I know the method, I can try this. Okay. L and R is equal to len of matrix. I know they're the same, so len of matrix, len of matrix. I can just go len of matrix. And just do this. Okay, so while L is less than R, so it's kind of like a 2 pointers. This can be done with a 2 pointers approach. A 2 pointers approach. Oops. A 2 pointers approach. 4 pointers approach. You know, this is technically a problem of math and geometry. Math and geometry. Is that right? I believe so. Okay. Doesn't matter. Okay. Okay, I should go back to this. Okay, so when L is less than R, N is equal to len matrix minus 1. Okay. Should I just make this N? Right, N is equal to len of matrix. Technically minus 1. Ooh, yikes. L is equal to 0. And R is equal to N. That's right. So len of matrix minus 1. Okay. While N is equal to len matrix. Okay, let me think. N minus equals 1 at the end of this. Does it? Or does it minus equal 2? Doesn't matter. Does it matter? Okay. L. This is matrix L. R. For a matrix, so top, bottom, top is equal to, I guess, the same. Bottom is equal to the same. Top left. Top left is going to be stored in a temporary variable. Matrix of bottom left, matrix of top left is going to equal to matrix of bottom left. Matrix of bottom left is going to equal to matrix of bottom right. Matrix of bottom right is going to be equal to the matrix of top right, and then top right is going to equal to temporary variable. That's a good optimization, I will say. Yeah. Slight optimization. Slight. Ooh, Sammy. Push cut. Thank you. A little bit. Appreciate it. It's a little bit flat, I would say. It's a little bit straight. Oops. I just like peeled off some of the wood. Okay. So that is there. I want to say that the next part of it is an index. So for I in range of, now what's this range? So it's R minus L plus 1. So this is including the right and including the left. So if you had 2 and 0, it would be 3 total. So you need 2 minus 0 plus 1 to get 3 total. So that's 3. So 0, 1, 2, 3. Sorry, 0, 1, 2. You'd get it here. So you only want 0 and 1. Okay, so you don't need this. Which means I is going to go here. So minus, okay, plus I, where it starts from 0. It goes to 1. And then so top left plus I is bottom left. Bottom left. Bottom left. Yes, bottom left. Bottom left. Bottom has to be minus I. And then bottom minus I. L. Bottom right. Right is going to be minus I. So then this minus I is going to be top right, top plus I, and then t plus I is equal to temp. Is that right? Top plus I feel like I made a mistake here. No, that's right. That's not right. Okay, this isn't right. This is L plus I. Yes. And so this has to be L plus I. And so you do all of that to move it in place. Right minus left. Until left equals right. But in this case you'd have 0, the 1, 1, n minus equal to 1. Does that really matter? It doesn't seem like it's something you care about. Because at the end of the day, what you really want to do is L plus 1 minus 1. Yes. Until when they're equal, you don't change anything. That makes sense. So I think this will work. Len matrix minus 1. You can remove that. Before I do this, oh yes. Sammy says, I'm in desperate need of a haircut. The winter growing has gone too far. Yeah, it's winter, hey. Possibly. And yes. Hello void. Let me run this and see. Okay. We got some acceptances. We accepted. We got accepted. We did it. Not bad. After looking at the solutions, of course. Looking at this, is this the exact same set of steps. So a temporary variable for I in range, top, bottom, temp equals matrix top L plus I. Matrix top L plus I is equal to bottom I L, bottom I L, matrix bottom R I. Same thing. Same thing. Very good. That's exactly the method. The 4 pointers. This is the this is rotating by 4 cells approach. Meow Meow wants to come up here. Maybe. Meow. Meow Meow. Trying to move me. Oh, she is good. She is good at jumping. Very high jumper. And she's very smart. Very smart cat. Oh, headbutting. So smart. So smart. Man. I wish I had a proper cat, man. One that I owned. Cats are just too cute. And some are just really smart, just like Fig. Aren't you, Fig? The Fig. The Fig is too smart. The Fig. All you can see is me rubbing Fig's body. All you can see is me rubbing Fig's body. The Fig. Boop. Booping. No, Fig. You dirty dog. Your snot. Don't put your snot. Okay. Well, that's it, guys. We solved the Leetcode problem. I'll just save this Leetcode problem and we'll be done. Holy shit. Daring. I think she scared herself a little bit. Maybe. Visual Studio Code. So we don't use Alacrity anymore, we're now using Ghosty. What are we doing? Okay, so we go to Leetcode, we go to nvim. Oh. We add a new problem. So the rotate image Leetcode problem. This is 48. Okay. Nice. We saved that problem, and this already was saved. Alright. Thank you guys for staying along for a little bit and just doing this stuff with me. So I appreciate it. Okay. I'll see you guys maybe tomorrow evening. Maybe at the same time. Peace.